All right, welcome to Calculus. So we're going to look at convergence tests. This particular aspect, there are lots of examples that we can work through. The biggest way or the most effective way I've always found to deal with the idea of convergence test is to keep a couple things in mind. First and foremost, we're looking for simultaneously the idea that the summation or the integration has a value of some sort. And what I mean by that is, since we're dealing with series, we're talking about the idea that if we were to add all the individual terms of this series up, we would get a number, and it wouldn't just continue to grow and grow and grow. Now, the underlying aspect of that is that the individual terms, as the n goes on, as the series gets longer, the individual terms themselves get smaller fast enough so that when you add them all together, you get a particular number, a exact value, as opposed to an unknown quantity that just keeps getting bigger and bigger. Now, with that as well, there's this idea that we know that the sum might converge, but this isn't necessarily directly telling us that we know exactly what the value is. That's a whole nother discussion. In some of these instances, we'll know what the sum is, but this isn't testing to find the sum. This is testing to find out if the sum exists. So the sheet I have in front of you, you can find this just about anywhere. You can do a Google search and you can find a bunch of them. You may have to pay for some of them. Some of them are free. This one in particular I found, I just grabbed, and it was free. This is almost verbatim out of a particular textbook, and I've used this for many years, even when I need to do tests myself. I do not have all these memorized. Some people might tell you you have to memorize all these, and so be it, but I do not have these memorized. The way these work is you identify, in the first column here, it actually tells you the type of test. So we have several different types of tests we can do. The second one is the type of series you're looking at, and then whether it converges or diverges, and any comments along the way. Now, I'll go ahead and tell you the nth term test. This is a test to see if it diverges. Strictly, that's it. That's all it will tell you, is whether or not the series diverges or not. It doesn't tell you if it converges. So there are two scenarios here. You find that the limit as n goes off to infinity doesn't go to zero. The individual terms are not getting smaller. You know this diverges because the values are not getting smaller. They may stay the exact same size, or they may be getting bigger, which means the sum is constantly getting bigger. But if those individual terms are going to zero, that we don't know what this series is going to do. We don't know whether it is converging or not. This is just simply a test to see whether it doesn't diverge. And this is always the first one I do because it's really simple. You usually look at 3 or 4 terms. Are those 3 or 4 terms getting bigger or smaller? They're getting bigger. Oh, we're done. We know this diverges. Oh, they're staying the same size. We know this diverges. These terms are getting smaller. This might converge. So then we move on to another test. The next 2 tests are the easiest ones to deal with, are your geometric series and your p-series. And a lot of people get these two mixed up, so spend a little time and focus on this. Your geometric series is like a exponential function. It means that you have some value here, and a lot of times we're used to looking at this and saying, well, the x is the variable. In this instance, the x isn't the variable. The x is just a placeholder for a particular value of some sort. N is your variable, okay? Now, here's the deal. It converges it only converges if that value of x, okay, is less than 1. If that value of x, the absolute value of that value of x, is greater than or equal to 1, then it converges, or diverges, pardon me. Okay, so this is one of those instances where we know it's pretty well cut and dry. And we also know that it converges to a particular value. So this is an instance with a geometric series where we know the exact value that it converges to. This is one of the few that we know this with, okay? And I'll work an example of geometric series. P-series is a little different. Here, the n is your base, and the p-value is your exponent. So this would be like a power series. Now, the way this one's written is kind of funky, and I've seen this written a couple different ways, but the thing you got it written is written like what's in front of you. And if p is greater than 1, then this converges. If p is less than or equal to 1, then this diverges. And we'll work an example of both the geometric and the p-series. And I'll have to do some of these others in another video, but they all work the same way. You look at the conditions. You look at the series and what you can do with it, like comparison series, limit comparison series, your ratio, your root. You just look at those different series there and just see what are the behaviors. Can you match up the behavior with a particular outcome over here in this third column? And then you should be able to determine whether it converges or diverges. Now, I'll tell you that the four most common ones that I've come across and that I use are your ratio test right here, okay, near the bottom there, your p-series, your geometric series, and then your comparison test, okay? In no particular order, but I will, the geometric and the p-series are the easiest ones, so those are always, I always go the nth term test, geometric, p-series, and then I go to one of the other tests. Normally my next go-to one is the ratio test, and then the comparison test if I can't do the ratio test. And most of the time, that will take care of 95% of all the series that you're going to need to work with. So let's just kind of jump in here with dealing with the geometric series. So the idea with the geometric series is that you have some value of x and it's being raised to a power, and that value of x is fixed. So let's just say we have doing the summation from k equal start at 1 and go off to infinity of, say, 3 times 2 to the n power. Now, in this instance, what's our value of x? Where the value of x is the base of that exponent. So here, x is equal to 2, all right, which is greater than 1. Now, we just go back and we say, well, what does the test tell us about that? The test tells us that if that value of x is greater than 1, it diverges. So now we know that this series right here diverges. All because we identified this was a geometric series because we had a base being taken to a variable power. Okay, so that makes it a geometric series. That base right there, that 2, that rate, if you will, is greater than 1. Greater than or equal to 1 is really what we want. We want it to be greater than or equal to 1. And we normally put the absolute value bars around it because it could be negative as well. But we want the absolute value of that value to be greater than or equal to 1, and it diverges. By comparison, let's just say that we go with k equal 1 to infinity, and let's say it's 4 times 1/2 to the, not the second power, I'm sorry, to the nth power. In this case, that x value there is equal to 1/2, which is less than 1. The absolute value of 1/2 is less than 1, which means that this series right here converges. And that's the answer we're trying to get after. Does it diverge or does it converge? We've answered it. Now, the thing about the geometric series is we can actually go through and we can finish this off and say we actually know what the sum is with the geometric series when it converges. And this is going to be the value of a, which is in this case is 4, and then 1 minus the rate, or that x value, which is 2. A lot of times I don't see that written as x. A lot of times I see that as written as r, because it's a ratio, a common ratio, if you will, between those values. So you get s is equal to 4 over 1/2, which is equal to 8. So the sum here for this one is equal to 8, which is one of the few instances, geometric series is one of the few instances when we can find that sum. Here we can't find this sum. We don't know what this goes to because it's going to keep getting bigger and bigger. So if you wanted to put an answer with this, you could say infinity. But that's really not, we're not really going to answer that. We're going to say it diverges, and we're going to leave it at that. Okay, now p-series. So what does a p-series look like? Well, for a p-series, remember this is geometric, right? For a p-series, we're starting with k equal to 1, and we're going off to infinity. And in this instance, we have 1 over some number being raised to some power, right? So let's just look at that series again. So it was 1 over n to the p. Now this one value, that can be, that I'll go ahead and tell you, that doesn't have to be 1. It can be any number, okay? It can be anything over this, but it really doesn't make any difference on this. So it's n to the p. So n is the thing that's changing, right? So n is the thing that's changing. That's our variable. So we're saying that we have some value. I'm using k here instead of n, so I'd use k. I guess I was using n up there. It doesn't matter though. So I got k being raised to the third power. So here my p-value is 3, which is greater than, well, what were my conditions, right? Look at the conditions again. So here it converges if p is greater than 1. It diverges if p is less than 1. So here my p-value is greater than 1, which means it converges. All right? Okay, well, what about if I have the summation starting at 1 and going to infinity? And let's just make the switch here simple. Let's make this k to the -3. Right? Well, again, we can go back and we can look at our conditions for our p-series. And here the p-series, it says if p is less than or equal to 1, it diverges. So my p-value here is equal to -3, which is less than 1. So, well, definitely less than or equal to 1, right? Which means this diverges. Now, this may seem backwards, that the negative value is going to diverge, but think about what this does. If you have 1 over k to the -3, that's the same thing as k to the 3rd. So you're dealing with a cubic function. Of course, the cubic function is going to get bigger. You're talking about a function, in this case, that does something like that. Now, this isn't a function. This is a series, of course. But you can always go back and think about what this would look like if it were a function. Over here, you're talking about something to the 1/3, or being raised to the, another way we could write that, pardon me, would be written like this. Well, you're talking about a rational function at this point. Now you're talking about something that probably looks somewhat like that. All right? So it's getting smaller, closer and closer to that x value. It is going to 0. You could do the nth term test. You can see fairly quickly that this is going off to 0. This one's not, which means it's inconclusive, which means we need to do another test. So all that is just to remember, to sum up. Those are two very quick examples. And p-series and geometric series are really straightforward. You just identify which one it is. Where is the variable? Where is it changing? For a geometric series, the variable is in the exponent. For a p-series, the variable is in the base. In both instances, you're looking at that other number and you're identifying what is the behavior of that other number, and that tells you whether it converges or diverges. P-series and geometrics are very cut and dry, very quick to gather that information and figure that out. And what that tells you, again, now keep in mind that what this tells you is that this is converging, right? And it's not really, I wrote this as a function. This isn't really a function, right? Remember, it's a series. So it's a series of dots. Right? It's a discrete definition, which means that there are distinct spaces between the individual values we know. And those values are getting smaller and smaller and smaller as we move on. That's what it means to converge. It's not just getting small, but it's getting small. It gets small fast enough. Okay? And that's the idea behind it converging, is it's getting small fast enough so that when we add it together, it's equal to a number, okay? Not some large quantity that keeps getting bigger. It's equal to a particular number. And in this instance right here, we don't necessarily know what that is, but we could, at this point, know that we can go find it. And that is quite useful to us. All right, so I hope this is useful. I hope you're starting to really love series. I do. I think it's one of the more interesting aspects of math, and there's a lot of things you can do with it. So keep doing math, or as I say in my classes, do more math, always do more math, right? And take care.